Hello, hi everybody.
Good evening, sir. Very good evening, sir.
Good evening. Can you hear me?
Okay, okay. Yeah, sir, I can hear you.
Okay.
ಒಂದ್ ನಿಮಿಷ ತಡೀರಿ ಶ್ರಾವ್. Very good evening. Hello. Sir, my voice is audible?
Yes.
Okay. Very good evening and a warm welcome to all the participants and the resource persons for the 6th day online ATAL FDP on RTOS and automotive CAN applications. So in the 4th day, we are going to have the two eminent resource persons with us. The first resource person is Brahma Chaitanya sir, who is an engineering director, DXC Technology, Bangalore. And another eminent resource person today is Syed Munib-ur-Rahman, who is working in Pi Square Technology, Bangalore. First and foremost, as I told you, I heartily welcome sir. Now I request BNR, that's BN Ravisimha sir, to introduce today's guest. Over to you, Ravisimha. Ravisimha sir.
Yeah, madam. Good evening, everyone. Myself, Ravisimha BN. It gives me immense pleasure, Assistant Professor, Department of EC SSIT. It gives me immense pleasure to welcome you all to today's sessions of our ATAL online 6 days FDP on Advanced Embedded System, RTOS, and Automotive CAN applications organized by Department of ECE, SSIT SAHE. We are truly honored to have with us a distinguished expert in the automotive field, Mr. Brahma Chaitanya Chiniwar, who has graciously agreed to be our resource person for today. Mr. Brahma Chaitanya Chiniwar is an executive engineering director at DXC Technology, where he leads a global team of competitive subject matter experts in business growth and technology leadership. With background of engineering in electronics and communication and automotive design, he leads the team to build state-of-the-art solutions for DXC's clients. Mr. Brahma Chaitanya Chiniwar has over 15 years of experience in automotive software engineering, and he has played many roles through his career and in leadership. He has extensive leadership experience. He has also built a development center for a German engineering company in Bangalore, which specialized in IoT product engineering and automotive engineering services. He also leads a large team, and he has also been a mentor, and he has also associated himself with many universities. In his free time, Mr. Chiniwar also spends his time with NGOs, running small programs like grocery bank, kids, education support, etc. And we are on behalf of the organizing team, SSIT, EC Department, SSIT. I extend a warm and heartfelt welcome to you, Mr. Brahma Chaitanya Chinivasa. We are truly privileged to have you with us today and look forward to an engaging, insightful, and enriching session. The topic for
Yes,
today's session is Auto SAR, Automotive Open System Architecture and Network Design. Auto SAR provides a framework for managing communication within a vehicle's complex network of electronic control units. It also enables a standardized approach to communication across different bus systems and facilitates the distribution of software components across various electronic control units while ensuring reliable and efficient communication. Once again, welcome and thank you for joining us. I also welcome all the participants of FDP to this session. Let us all now join in welcoming our esteemed speaker with a virtual round of applause. Over to you, sir.
Okay. Let me one moment. Thank you very much for giving me this opportunity to connect with all the faculty from various universities, various colleges. It's really a pleasure and an honor. I got associated with SSIT when I was when I visited SSIT for one of the programs a year or so ago. And when Madam called, I immediately was very happy to be part of this program because there is so much of there are so many things that come from the industry that keeps keeps getting updated, and especially now we are living in times of technology related updates happening almost overnight. As you know, AI has come when DeepSeek came was announced. It's already overnight things changed. So the same kind of tectonic shift is happening in the automotive industry as well. So that is where it is very important for all of us to understand what the industry needs and also guide our students in that direction. I myself, I very much am involved in student program development in our company. We keep pushing to have mentorship programs where we have students who join us, have a mentor who will train them through the on like an on-job training. And we are also looking at different programs that universities and the government is taking initiative of, so that we can we can bring in new talents from the universities into our organization. Like sir said, I have been in automotive industry since almost about 15 years now, and my career my career started in around 2010, where I joined a company called KPIT as a software engineer, and started working on AutoSAR. So I always say, on a funnier note, that I am born and brought up in AutoSAR. So my career has always been in and around AutoSAR, and AutoSAR itself is evolving so much nowadays, which is also challenging times for us, considering the way the market has been going. And with that, now I work with DXC Technology. I work as an engineering director here. I support the team of development that happens out from India, as well as I work with a global team to look at newer technologies, to explore them, to do POCs, to understand how they can help us in different new ways of how the automotive industry is going and how we can be in business in the area. Having said that, I'll start with sharing my screen. I have put together a few slides about what we are talking today. I have not restricted myself only on the AutoSAR and the network design. We will touch base upon that more or less, or majority portion of the topic of the session. But I also have a bit of information of how the industry evolves and what kind of future are we looking at in the software world of automotive industry. I hope that will also give us a challenge to to explore those technologies and bring that to our students. Let me share my screen. I would need just 1 minute. Okay. Please let me know if my screen is visible.
Yes, sir, it is visible.
You see a full screen PowerPoint, correct?
Yes, sir.
Yeah, okay. Okay. Let me, yeah, okay. So today we are in this particular session. We will talk about AutoSAR network design, and I also see that you all have gone through a lot of sessions already on CAN communication, RTOS, how ECU design is done. So if there is anything that is overlapping, please do let me know. I can cut short on that if it's already covered. Yeah. Yes. So in today's session, we will talk a little bit on automotive industry. We will talk about AutoSAR, the two types of AutoSAR predominantly, which are classic and adaptive, automotive networking, automotive future, how the software world looks like, and sometimes on question and answers if there is anything that I can answer. Yeah. Okay. I've started with a very, very old slide, this one, but it gives a very good gist of how complex the automotive software system is nowadays. So automotive software has evolved in a quite a significant over 100 years, from a pure mechanical system which was designed to a lot more software controlled system. Hence, with that evaluation, the product complexity has come out a lot in automotive industry. So every part of the car is now controlled by software, and this is already in the past. What I'm saying is something that is already on the market since 10, 15 years already, right? So, but now it has even gone, even gone further. Just to give a highlight, for example, instrument cluster, the cluster that we see in the car displaying us the time, speed, and the indicators whether there is a problem with the car and everything. This is completely controlled with the software. The engine control is completely controlled with the software. The cruise control, adaptive automatic braking systems. The latest cars like the Mahindra BE6, it has a automatic parking system. So there is a lot of sensors and actuators that are working around to make to bring this the feature into the car, right? So that is where it becomes important that the technologies that are used in building these systems, this understanding comes to the students pretty well. Yes. Yes. I've just highlighted a few of these, which are very software driven. I think ACC has become a common feature now. Engine control, as you know, every bit of how much fuel is going in, how much air is going in, is completely controlled by software through various calibrations. And Yeah, and then the ECU is fine-tuned, for the performance of the car. So many variants of the cars come, so each variant will have different types of tuning that is needed. If these companies, if the car makers had gone for different systems for different cars, it would have become a very expensive affair. So that is where software comes into picture, where you can calibrate, where you can fine tune these parameters such that you also look at the costing aspect of it, that you have one ECU or one hardware, one set of software, but very many variants of the software in order to control the software behavior. One of such very nice example I always take is the mirror ECUs or the door ECUs. Even better, we have 4 doors in the car. We don't need 4 different softwares to manage or 4 different types of ECUs to manage that. You can always have one ECU, one ECU product manufacturer, but you can put 4 of that in the car, and you can say that, okay, the behavior of the software should be front left for this door, rear left for this door, the same way the other side. So what we are doing by doing that, we are controlling the number of hardware pieces to be managed, number of units to be managed, especially in the production line. So there is only one line of units from where four ECUs can be picked up rather than 4 different lines. And from the software, it is very simple. Depending on the position of the ECU, software automatically detects whether it is for front left, front right, rear left, rear right. So with that, the behavior of the ECU changes, and during the software development also, you develop this one time, and then you can deploy that for 4 different use cases. So with that, the production line costs are managed, the development costs are managed, the storage costs, the transportation costs of everything gets managed. So this is how the software complexity helps also in the pricing and the way the cars are built. Going from here, this is another picture that I wanted to bring, how complex the internal things of the car would be. We don't see this often, but you can see that the red marked parts that you see, these are all the wiring harnesses, the different sensors that are mounted in the car in different positions. If you have a sunroof, there is a sunroof. There is a sensor that is monitoring the sunroof. Here you have engine control related sensors. Here you have bumper related sensors. Here you have tire pressure monitoring sensors, etc. Right. So this also leads to a lot of complex the wiring design within the car, and there is a special bit of engineering research that happens especially for this, because even a couple of inch of length of the wire, or the weight of the cabling that goes into the car, if that is reduced, it leads to a massive advantage for the manufacturer. It leads to weight reduction of the car. Weight reduction is proportional to the efficiency of the car. So fuel efficiency comes into play. So there is a lot of engineering work that goes on designing this. Like, for example, where would I position my ECU? Where would I position my sensor? Do I position it in the front? Do I position it in the rear? How does that ergonomically balance how does that balance the weight distribution on the vehicle? All of these has its own in-depth engineering that happens, and that is where the network design topics and all are very critical. How I am designing the network, how am I designing the cabling. Right. So one example that I want to give, this was, I think, in 2014, we had an issue with the car but the charging was not happening sometimes whenever we were testing in the garage, and we took a lot of debugging effort, because as you see, charging is not working. Sometimes there are glitches. You immediately go and see what is the problem in the charging ECU, what is the problem in the charging battery management system and all. Right. So, but when we went on to spend a lot of time in debugging this, what it came down was the positioning of a cable, the insulation of a cable, it was very close to a heating element of the car, and because of that heating element, the wiring had a specific insulation inside it, which was not good enough. So it was distorting the signals that are passing through it, and because of that distortion, the data that the charging unit had to receive sometimes was not proper, and the whole vehicle behavior was impacted. We literally tore down the car to see where is the problem coming by cutting the cables, by hooking oscilloscopes to measure, and then we realized that it was just a bit of extra insulation that a cable needed, especially in that portion of the car. It solved the problem. It turned out that it is not a software problem at all. So you can imagine how complex the system is, right? Yes. Yeah, having told about the number of ECUs, the complexity of the ECUs that are there, and the complexity of the vehicle harness and the cabling that are there, I wanted to start the next portion with how the industry and what the industry is at right the moment. If you see the trends, what is happening in the industry, this is very important because what you are doing is a very noble job of preparing students to face the real world when they come out of the engineering, to get a job, to understand what they are doing, and to make themselves an expert there. That means they should know that what is the trend of the industry that is happening, and what do they prepare. These are different trends that are happening in the industry. I think electrification is a very it has become the talk of the town in India also, particularly even with the two-wheeler industry. You see that there is a lot of electrification work that is going on. So because of that, there is battery management technology, solid-state batteries for better range and safety. This is one of the industry trends that is there. So there is a lot of research that is happening in the EV industry to bring out the best range from the batteries, to bring out how these high voltage systems are managed, and also, of course, the infrastructure that is needed for it. Autonomous driving, self-driving cars, this has been an increasing demand, and also has a lot of regulatory challenges. Some of the companies have been able to achieve. We have level 1 to level 4, level 3, level 2.5, level 2. There are different types of autonomous vehicles. Some companies are able to already achieve it. Some are still through the process. But in India as well, if you see, there are a lot of autonomous assist. If not, it is the completely automated car, but assist to the driver. There are a lot of features that are coming, right? So lane keep assist. So if there is a lane change that is happening, there is an assist that is coming in. For cruise control, there are features that are coming in. Emergency braking system, and auto parking is one such example, with the one that you have in Mahindra. If you see the Tesla, it has a highway autopilot feature where the driver has to be there, the driver has to be alert. It is a prerequisite. The driver is monitored as well. But you will see that on certain countries, in certain highways, the Tesla can completely drive automatically through for a very long stretch. So this is many companies that are trying to do, and this is a trend, and this is where there is a lot of job opportunities in future. Connectivity and software-defined vehicles. Software-defined vehicles, I'll touch base upon this a little bit later. But software-defined vehicle, this is how the market is going right now. As you see, our cell phones, right? So our cell phones are all it's like everything like a supercompute platform on our hand. So the car industry is also going that way. You can imagine, a system that is updatable, a system that is what do you say? A system that is where you can install features on the go. You have variants that is possible. You can subscribe for service. So in the phone that we can do that, right? So in the phone, for example, within an app, I can purchase certain services. I can install an app myself. I don't need to take my phone into Apple Store to get some new application installed or new software upgrade to happen. Now, over the air, I can have the operating system of my phone updated whenever the new OSs are released by Android or iPhone or Apple. The same way, even in the cars, the software-defined vehicle trend, how is coming is that the cars are upgradable automatically. You have parked your car, put it on the charging. The vehicle knows that it has enough charging done. So it will talk to the cloud. It will check if there is any software updates for certain features that are to be pulled in. Then it does that automatically. It updates the system, and when you come back, it gives you a prompt saying that, hey, your car is now updated and it has the following feature. You can subscribe to various features like BMW in their cars in European countries. They have this heating subscription wherein you can subscribe. You can trigger that you want the car seats to be you trigger the car seats to be warmed up before you come down to pick your vehicle, because it's -5 degrees or -0 degrees or -10 degrees temperature. You don't want to go directly sit in a completely cold car. So you can preheat the car so that it is ready for you when you come. But maybe when you go, you want a certain temperature setting, but if someone else in the family, let's say wife goes and she has a different temperature setting that is needed, the profiles are maintained. So if you are the one who's asking the car to be ready, it will set everything for you. If the other person if the wife is looking at taking the car out, then the temperature settings is different. Then it sets the temperature setting accordingly. It sets the music accordingly. So all of that, and to do that, you need more software defined features coming into the vehicles, and that is where the connectivity and the software defined vehicle trend is quite high. And connectivity also means that the car is always connected to the cloud. It is connecting to the infrastructure on the highway. It can get automatic alerts from the police if there is a problem on the highways. Let's say there is an accident, then you get that notification saying that, okay, 50 kilometers down the lane there is an accident. There is a pileup of traffic. These kind of alerts can come in automatically. And then you also have AI-based chat systems now. A lot of Chinese cars are coming up with where you can converse through when you are driving, asking questions, asking the car to change the settings rather than you doing the settings, etc. That is very important trend that you see in the industry. You have sustainability. There is the push to reduce the carbon footprint, as you know. So because of that, all of the car manufacturers are looking how to be sustainable with their materials, with their recycling, the kind of wastages that are coming during the manufacturing. All of that, they're very much focusing on those topics as well. Advanced safety. I don't think I have to explain that very well. If all of such features are coming with autonomous drive, software-defined connectivity, and all, the safety aspects becomes the key critical thing. The software or the air update should not trigger wrong behavior in the car. There should not be a wrong behavior triggered when the car is getting driven. autonomously, right? So so there are a lot of safety standards that are getting implemented. That is another area in which there is a lot of job opportunities in future. And then mobility as a service, shift from flexible vehicle usage models beyond ownership. So I rent a vehicle. There could be a robo taxi. I'll just book that taxi and it picks up and drops me. Uh, Ola, Uber, kind of facilities, right? So rather than owning the car, I can always look at subscribing for a car. I can look at hiring a taxi, right? So there is a lot of shift that is going in this direction, because owning the car also could be very expensive. And that is where the mobility as a service is another trend that is coming in the industry. Just a quick example of how it looks like in the newer ways the cars are operating. So that in the initial pictures you saw a very traditional one, but in the newer one you have remote repair possibility. You have a cloud. Through an edge instance, the cloud is talking to the car. It has a software over the air update feature where it is pulling in different software updates. You have different high performance computers, not just ECUs, really almost like a supercomputer sitting in the car, running a lot of computation. Then you have the software development cycle where you are developing the software, you are pushing the updates to the test vehicles, and after the test build, you are making a campaign to release the softwares to be updated into the car. And then you have different communication. V2X is vehicle to anything communication. It could be vehicle to vehicle, it could be vehicle to charging, it could be vehicle to other infrastructure, it could be vehicle to the service cloud. And then you have also your mobile apps. Through this mobile app, you control what you want to happen in the car. So this is exactly the direction in which the automotive industry is going, and all the technologies are getting upgraded to handle this amount of complexity. Earlier, uh, there was no software over the air update 10 years or so ago, right? So you had to take the car to the garage, and then if there is during the service, if there is a software update due, the service engineer would connect the car to OBD port, and he would program the car, and he'll make the update. But now it can happen seamlessly when you are picking up a coffee, parking the car near a cafe. The car can get updated. It is that is the kind of future we are looking at. Yes. Here I will stop with the introduction to the automotive industry and the kind of trends. At the end, I'll come back onto what kind of technologies are relevant for us to look at, right? And now I will move on towards the AutoSAR part of the session. Yes. As you know, AutoSAR is a consortia. It is not a company in itself. AutoSAR has been developed with all of these automotive companies coming in together. So what happened? Why AutoSAR came into picture? There was a lot of that software development that was happening independently, and there was no reusability that was happening, and there was a lot of dependencies for the OEMs like BMW, Volkswagen, Daimler, Ford. They were very much dependent on other companies who would bring the software or bring the entire ECU, and OEM is original equipment manufacturer, right? So they would just assemble the components, put together, and they test that, and then they make the car. They did not have control on the software that was running on the car. It was coming from different vendors. Only the core key technologies for maybe engine control and all those were controlled by the OEMs. The OEMs also did not want to be, to have an ecosystem where they are heavily dependent on someone else. So what they did, they said that, okay, let us form this consortia. We will bring partners, and these partners through these partnerships, we will develop a standard which is scalable, which is reusable, and which also creates a good independent supply chain, where the hardware is abstracted, where the application development is abstracted from the lower layers. So if you need to really move a feature from one ECU to another ECU, because in your design you see that the feature running on one ECU rather than two different ECUs gives us an economical advantage. That did not mean that you have to do a completely whole new development. The applications could be ported from one ECU to another ECU. Had there been a separation from, sorry, yeah. Had there been a separation from the hardware, had there been a separation from the lower layers of the software, and the application focuses more on the business logic rather than setting a configuration pin of the hardware, right? So that way, AutoSAR. That is how AutoSAR came into picture. This consortia has a lot of different types of membership, as you know, the core partners, the premium partners, the development members, and these companies put together, they contribute to the consortia. In the classic AutoSAR world, we will talk a little bit in a few minutes. In the classic AutoSAR world, what our AutoSAR consortia did is to define specifications for different software modules, define how the architecture would be, and make it very configurable. So I take the same software, I say the same architecture, and I can configure that for an XP chip, or I can configure that for a Infineon chip for the lower level. I can configure the middle software or the base software for a use case for a autonomous drive car, drive ECU, for a infotainment ECU, for a door ECU, for a mirror ECU. The complexity are different, right? So if let's say if you take a door ECU, you don't have so many controls in the door. Maybe you need like 50 signals to be configured through the stack. We'll talk about what is the signal later. 50 signals to be configured in the stack, and whereas gateway ECU, which is like exchanging data between different ECUs, becomes like a central unit. It has to have probably 2,000 or 5,000 signals to be managed. So for that, you don't have to change anything. You can just reconfigure the stack to be able to handle about 2,000 signals, or you can configure it to handle 1,000 signals, 100 signals. So with that, the software standard what the software standard is ensuring that everything is as per the defined requirement. You are just scaling or descaling depending on the need of that particular feature or the particular ECU. So this gave a standardization, and this brought in vendors like Vector, KPIT, EB, ETAS, who built those standard softwares, which were integrated by tier ones, where the tier ones would take the software from them. The tier one would configure the software based on the ECU. Let's say it's a braking ECU. For the braking ECU, you're configuring 1,000 signals. So those signals are configured. Those sensors and actuators are configured and implemented. And then on top of it, you implement the braking functionalities. So when you build the braking functionalities, today you are building on one microcontroller, let's say from Infineon, and tomorrow you need to change that microcontroller to Renesas microcontroller and an XP microcontroller. It doesn't mean that you are changing the braking logic, but you are changing the lowest layer of the hardware abstraction layer, and reconfigure the pins, reconfigure the MCAL layer, such that all the needed data for my braking functionality to work on an XP chip instead of an Infineon chip. So this saves this, if you can imagine, it saves a lot of effort and bandwidth and of course the timeline in which you are operating with different vehicle releases. you are not reinventing the software again and again. You are breaking the software into multiple areas so that you can manage the pieces independently. So that is the kind of flexibility which AUTOSAR AUTOSAR as a platform brought. But AUTOSAR, like I said again, it never got into creating its own software. It created specification in the classic AUTOSAR world. And in the adaptive AUTOSAR world, we will see it in a few minutes. It created reference implementation so that the reference implementation can be taken. You can already start doing your POCs for let's say you are bringing up a new feature and you want some tests or some checks to be done. You are just taking the reference implementation, you are making your implementations on top of it, you test, and then you take it to the production level through a production grade software. So AUTOSAR did that because there was a demand not just to give specification, but to already give an implementation that can be used and not wait for the whole implementation to happen from one of these standard software providers. Right. So this is how AUTOSAR Consortia works, and AUTOSAR Consortia came up with two different AUTOSAR types. One is the classic platform, one is the adaptive AUTOSAR platform. The classic platform is more MCU, the microcontroller based, really strong, strong real-time requirements, very core embedded electronics, whereas the adaptive AUTOSAR came up with kind of service-oriented feature running on Linux. It is safety critical, but it cannot ensure because it runs on Linux kind of platform, which is POSIX. It by default cannot ensure that that it is as strict a real time as a microcontroller would be, and it would and this would go on microcontrollers, and this would go more or less on the microprocessors. As you see here, I'm just going bottom up. Deeply embedded ECUs were the target for classic AUTOSAR. High computational power ECUs are the target for adaptive AUTOSAR. We saw a couple of slides ago how there are different high compute platforms that are coming into play. The vehicle already has teraflops of compute power sitting in it, and a lot of data of different sensors are processed within this car itself rather than doing it outside the car. So you need high computational power ECUs, and you need platforms on which you can do that. You cannot do that on a microcontroller which has a very small memory footprint. You need really large memory footprint ECUs. You need very large computational power ECUs. You need accelerators, like NVIDIA has CUDA for processing. You need accelerators to do so, right? So the target is very clear. Adaptive AUTOSAR targets the high computational power ECUs, whereas the classic AUTOSAR targets deeply embedded ECUs. First released in 2004, 21 years ago. First released in 2017. This is the way where the trends of the industry changed, and that is where the new platform came into picture. Here you will get only the specification documents. Here you will get specification and code, which is what I said. The reference implementation is provided by the consortia here. Same address space for all applications. Each application has its own virtual address space and MMU support. So what I don't think I'll not go into the deep of embedded systems. I think the previous sessions would have covered it. Same address space, you have limited RAM, ROM, and all of your applications are going into that specific flash area. Whereas here, each of it can have its own memory space. So it's the basic POSIX concept that each application runs as an independent unit, right? That's a fundamental difference in which shows what kind of chipsets on which you can run a classic AUTOSAR and what kind of chipsets you can run an adaptive AUTOSAR. Execution from ROM, application loaded into RAM. So RAM execution happens from the RAM here. Here the execution is happening from the ROM area. The code base and all is from there. Safety up to ASIL D. If you are familiar with functional safety concepts of automotive, there is ASIL A, B, C, D, D being the highest safety compliant, whereas, for example, a braking ECU should be a D safe, because if the brake doesn't work, the fatality is different. The airbag ECU will be a higher safety compliant, whereas adaptive AUTOSAR has up to ASIL B, so it cannot be used for a braking ECU, for example, but it can provide up to ASIL B. So ISO 26262 is the functional safety specification specifically for the automotive industry. If you have time, please just go through online about what are the different safety levels and what do they mean. You'll get a very quick, brief introduction of what ASIL A is, what ASIL B, what is ASIL C and D are. Here, moving on from that is the classic AUTOSAR is a very signal-based communication. Here it is a service-based communication. We will talk a little bit later on this, but fundamentally how it works is you already have a pre-described number of signals here that, okay, I have seat occupancy signal. So whenever the passenger the driver is sitting and the co-passenger is sitting, there will be a signal configured to say whether they have the seat is occupied or not. And this is needed for many various features. You can use that signal to say whether you want to detect how many passengers are there in the car, right? So if you have heating elements, you need to make sure that seat heater works only when somebody has occupied the car, not other time, right? So it's very signal based, point A to point B. You would pre-configure that, okay, ECU1 sends a signal and ECU2, ECU5 receives that signal. And if you need to change that, it is not possible. It is a point-to-point communication, and you have to design your system such that is where the network design part again comes into picture. The network designers in these OEMs, they really clearly define how many ECUs are there, which ECU has what functionality, which ECUs has how many CAN signals that are transmitting it is receiving, which ECU has how many Ethernet frames, how many LIN signals that are transmitted and received. This is already the network designer looks into all of that, so that there is an optimal load on the network, and they even simulate this to know that that kind of exchange of data doesn't overload the bus system of the car, right? So in the service oriented communication, it is a little bit different. It is like, let's say I am one of the service provider and I have the vehicle speed, I own the vehicle speed service, and you have another 5 ECUs which needs the vehicle speed information to do some processing. Let's say the parking ECU really needs to know whether the vehicle is at 10 kmph or whether the vehicle is 100 kmph. Parking is not needed at 100 kmph, but whereas parking feature can be activated at a 10 kmph speed, because that's at the lower end of the spectrum of the speed, right? So I, as a ECU, I broadcast that, hey, I have a service that I can offer you every 10 milliseconds, or depending on the frequency we agree, I can offer you the vehicle speed information. And then the other ECUs can decide to subscribe for this service or not. So if I need if I'm a cluster ECU and I need to show the current vehicle speed, I will subscribe for this service, and I will keep getting the vehicle speed information. Then I will use that for my processing. If I'm a parking ECU, I will subscribe it. But if I am a If I'm a temperature control ECU within the car, if I'm a HVAC control ECU within the car, I might not need the vehicle information, the current speed of the vehicle at all. For me, I need to know the temperature outside to ensure that I have optimal cooling inside. Right? So I won't subscribe for the vehicle speed, but I will subscribe for the temperature service as an example. So that is how the service-oriented communication concept came up, which is where you have flexibility whether you want the data or not want the data, which is a little bit different from the traditional system, right? And then finally, the operating system. This classic AutoSAR it runs on OSEC, being the base operating system, and has its own operating system called AutoSAR OS. And adaptive AutoSAR runs on POSIX compliant operating systems, Linux, Safe Linux, QNX. These are the different examples. Then the language in which it operates. So this is purely C programming, and here you have maybe at the lower layers a bit of C programming, but more or less in C++ 14 and above. Yeah. A few things about just another slide a little bit that talks about classic and AutoSAR a little bit more in detail. Here it is purely based on configuration. You configure CAN stack, you configure FlexRay, you configure SumIP, you configure memory, configure diagnostics. You have different fault configurations that you do. So everything is configurable here, and then you configure, then you integrate and deploy. So you have base softwares and RTE runtime environment for application and base software to talk to each other. Then you have different ways of testing the software, and then of course the safety, ASPICE processes, etc. On here, it is more of a service based, like I explained. You define APIs rather than really fixed functions. Extension of function cluster based on OEM software platform requirements. You can migrate some of the features that are non-critical and can run on a service-oriented design. You can migrate them from classic to adaptive, and then you have different tool chains that there are different tool chains that come to play in order to make these implementations happen. Vector is one of the companies that provides the software and also the tool chains like DaVinci Developer, DaVinci Configurator. Electrobit is another company that provides Tressos kind of tool. And then you have different testing tools that are coming from DSpace for testing these VCUs, etc. Okay. I will jump next to the classic AutoSAR part. So the AutoSAR software architecture, right? So the classic AutoSAR, if you zoom in a little bit, it has different types of different types of interfaces. You have different types of services, the communication, abstraction areas. At a broad level, it looks classic AutoSAR looks like this. I have a couple of slides later. I have another set of slides which will talk a little bit more in detail. For example, now we go on to the ECU hardware. So let's say it has a microcontroller, it has a few sensors connected to it, it has some transceivers connected to it. So first is that we abstract all of that hardware related topics such that these upper layers don't even really have to know what is the underlying microcontroller. So that is where you have microcontroller abstraction. So here you abstract everything about that particular microcontroller, and then you give standard APIs or standard interfaces for communicating. Like, let's say I want to send a CAN message. I'll just call CAN_write API. I won't care whether it is whether the underlying ECU is a Infineon ECU, or underlying ECU NXP microcontroller or Infineon microcontroller. For me, it is if I want to send a message on CAN, I just say CAN write. That's all. Right. So that is where the microcontroller completely gets abstracted through the microcontroller abstraction layer. Then you have the ECU abstraction layer. Of course, it's not just the microcontroller that is there in an ECU, right? So you have different peripherals, you have different GPIOs to be controlled, you have different sensors to be that we want to talk to. So there you create an abstraction layer for the ECU related part, not just the microcontroller related part, and provide interfaces such that I can talk to a GPIO to control a valve. Then I have a standard interface for that, right? And then for the communication, you have CAN communication, FlexRay, Ethernet, LIN. FlexRay is not used anymore, but it's also one of the predominant protocols in automotive. So for the communication protocols as well, for example, we took this seat occupancy as one of the signals, right? So let's say I'm this one of the software components here in the application, and I need to detect whether the driver seat is occupied or not. I just need that data. I don't really need that data. I don't really need to know as an application component guy whether it is coming on CAN or Ethernet or LIN or FlexRay to me. All I need is that particular signal, right? So I completely abstract that whole protocol section here in the communication area. And under this, I will deal with CAN or Ethernet or LIN or FlexRay, most protocol, whatever. But here I just give standard interface to read a signal. So if this component wants to read a signal, it says read the signal and it gets the data. It doesn't care whether it is coming from which protocol, right? Or it doesn't even care whether that seat occupancy is detected within this ECU or it is coming through an external ECU through such a CAN protocol, right? So that is the level of abstraction that we provide that comes here. And then you have shared services. You need to log a fault. You need to read a specific non-volatile memory. You need to set the watchdog whenever there is a problem in the ECU. The watchdog should take an action. So these are different standard AutoSAR services that are there, and that are also abstracted. You have standardized APIs through which the applications can interact to set a fault, to log a fault-related data into non-volatile memory, etc. Then you have the operating system, and the operating system has its interfaces for scheduling, for memory protection, and lot many operating system features. So now, if you see, so what we just discussed is that there are different layers of abstractions that are coming into play, and the applications are independent. Now, if I want to move this application from ECU A to ECU B, I really do not have any dependency on whether my feature runs on this ECU or a completely different ECU. My dependency is that as long as I'm getting through my interface the signal, the data that I need, the occupancy data of the driver, my application can do anything, the processing independently of that, and need not really look at what ECU it is working on. So this is the kind of abstraction that comes into play. So now you can imagine how the development process of this works. This application developer can develop his application independently. This base software guy can configure his communication stack independently. Another application guy can completely develop his application independently. And then an integration guy comes into picture who puts everything of this together and makes the software work. So that is where the interface definition in AutoSAR becomes very, very critical. So if the interfaces are not defined properly, then there is a problem that you are expecting a data and that interface, that related data is not coming to you at all. And to do all of that, the AutoSAR runtime environment, which is one of the most complex softwares that I've seen, comes into play. It's a very complex software to understand, but it's a very complex, very simple if you understand it, you can break down that into a very simple understanding as well. So it doesn't look complex after that. But initially, this is a specification that has what 3,000 or 5,000 pages. So it looks complex, but it does a very beautiful abstraction of the upper layer with the lower layer, so that these developments can happen independently. Right. Initially, when I introduced about AutoSAR, I was telling that OEMs wanted to build their own software as well. And now, two of these blocks can come from BMW. Two of these blocks can come from Continental. Two of the blocks can come from another company. This whole base software can be configured by the fourth company. Complex device driver can come from a fifth company. But you can put all of these together and make a ECU work. So that is the beauty the AutoSAR is bringing, right? And if I'm let's say if my company is a very good company in motor control algorithm development, and I have the best optimized motor control, and then I want to specialize in that, I want to stay in that area, I don't have to worry about all of these things. I can be a very specialized guy here. My components will be bought by, or my software will be bought by different integrator like the OEM or tier one. They integrate it, and I make my business through the expertized motor control, but I don't really have to focus on the other areas. So that is how there are many companies that are doing this expertized targeted implementations, which are and they build a niche business around it. Yeah. This is a very simple view of one ECU, right? So now that ECU, from all the complexities that we discussed about, is really expanding beyond, in the sense that we spoke of classic AutoSAR and adaptive AutoSAR. Here you can see that within a high performance compute, you have a safety microcontroller on which a classic AutoSAR is running. And then you have a SoC on which you have a hypervisor, POSIX OS, and then adaptive AutoSAR running. Then you have a common middleware, and then you have applications of autonomous drive running. The same way, if I switch to the middle one, again I have a classic AutoSAR, again I have a hypervisor, but here I also run adaptive AutoSAR, but I also run an Android, because in the infotainment now there is Android operating systems come into picture. Then I build my applications that are Android automotive specific or the infotainment specific. Then for mobility, I can do telematics ECUs also, right? So, but what is the common part that you see? Irrespective of what is the different type of ECU, you can still have this middleware common, which can be configured based on the different use cases, and that is what AutoSAR brings. But that is also the complexity. Okay. That is also the complexity that we are dealing with. So you have multi SoCs that are coming into a single ECU. You need to make sure that all of these operate together. Yeah. Another example. Now here, just let me. I do not know what happened here. Yeah. Okay. Yes. So if I go back a little bit, here we are talking about one single ECU with one single classic AutoSAR setup. Here we are now going a little bit beyond into complex systems. From here, we'll go beyond into, not just within ECU, the outside ECU areas as well. So here, in-car systems, private cloud and backend systems, development platform. These all have to come together because of the way the software-defined vehicle ecosystem is evolving. Yeah. So you have the in-car. So far we spoke about in-car. So you have the operating systems, classic AutoSAR, adaptive AutoSAR, etc. running. You have ADAS, you have AIBI, body motion type of ECUs. Now, they are always talking to the backend. That is where you have the connected car, you have advanced diagnostics where you can diagnose what is happening in the car. You have some aftermarket campaigns that you want to run. So then then you are collecting certain data, you are sending certain data, right? So software development, software over the air updates and stuff. So that is where the cloud backend connection and the in-car comes. But then from here, you go into the development platforms. So let's say you are collecting a lot of data on autonomous drive. You can build a machine learning system on your backend where you use the exact same data coming from the car to train it so that your algorithms become better, right? Then second is you want to do the software development, not make software releases once in 6 months or so, but you want to provide software updates to going in the car every month. Then there is a whole life cycle of the software development that has to happen. You develop here, you test here, you deploy it onto the cloud, and from the cloud, you through the software campaigns, you deploy it onto the car. So this is the kind of ecosystem that is getting evolved. So all of the cars that we will see in the future will have the faster turnaround time of feature delivery and a much complicated system of execution like this. I would recommend, if you have not seen this YouTube video, if you search in YouTube about Mercedes-Benz MB.OS launch, there is I think 45 minutes to 1 hour video of the Mercedes CTO talking about how Mercedes is implementing their future car technologies. It is really very interesting, and you will see how the chip to cloud story comes out and stitches together with what we are discussing right now. I would highly recommend to watch that video. Yeah. This is a repeat. Considering, okay, we have half an hour more. Okay, I'll try to finish in another 15 minutes or so, but feel free to ask me questions. We can spend some time so that we can interact, and it is not just a one-sided, rant. We spoke about the different layers, and the different layers get broken down like this. You have microcontrollers, you have communication-related drivers, I/O drivers. On top of communication, you have the communication hardware abstraction. On top of that, you have communication services that completely abstract the protocol. And then you have RTE through which the application talks from a communication point of view. From a memory service point of view, also, it's the same thing. AUTOSAR through RTE, the modules talk to NVM. NVM will talk to these modules through the layers to be able to store the data. And then you have system services that we spoke of, the sleep wake up cycles of the ECU, the fault logging of the ECU, the watchdog. All of that has its very specified defined layers in AUTOSAR. So you have the MCAL, you have ECU abstraction, you have communication services, system services, and other services. And then you have RTE, and then you have the application layer on top. Right? Quick example of quickly a little bit getting into the communication part. Let's say you have different ECUs in the cars, and you have a gateway. So now I want to talk. I want to send information on our CAN message from ECU 1 to ECU 4. So I'll have a transmit message here, and I'll have a receive message here configured. And then the transmit message goes through the bus system. Then there is gateway, which puts that from one CAN bus to another CAN bus, because you cannot have all of these ECUs connected through CAN buses independently. So that is where the gateway concept comes into picture. So it takes the message from here, it receives the message on bus 1, it gateways that message to bus 2, and then it puts it onto and the ECU 4 receives that message. So based with that, certain functions are implemented here, certain functions are implemented here, and the data exchange happens. How that happens is that you receive a message, the CAN driver receives it, it tells the CAN interface, the CAN interface provides it to the PDU router. The PDU router then sees whether it is a routing message or whether it is any receivable message. If it is a receivable message, it gives it to AUTOSAR-COM, and AUTOSAR-COM gives it to the application layer. The same way, the other way around, from there, the signal comes from transmission message, signals come from COM, COM puts that signal into a PDU of 8 bytes. It's basically an array of 8 bytes, you can imagine. And that array of 8 bytes will be given to CAN interface, and CAN interface puts that into CAN driver and sends it out. Now we spoke of quick gateway here. So how the gateway works is CAN bus 1 receives the data through the CAN transceiver to the CAN controller. It comes to the PDU router. PDU router then sees that, oh, this message is not for me to consume, but for me to route this message to another controller. So it gives the message back to CAN interface. CAN interface sees that, okay, this is given to controller 1 to controller 2. Sorry, this had to be controller 2. So the message goes from PDU router to CAN controller 2, CAN transceiver 2, and to the CAN bus 2. Right. So that is how that is how the message gets transmitted routed. I think this part of the session has already been covered in the details of the CAN message. You know what are the different fields, the payload and data field, the sequence of the CRC that are calculated. I will skip this. Yeah, I think if this is also covered, I will skip it. But at a very high level, we spoke about two words there, signal and PDU. That is very, very important to understand if you are working in the automotive CAN communication area, right? So for an application, it is a signal. We'll take again the seat occupancy signal. So this ECU wants to transmit the seat occupancy data on the CAN network. So it will give that signal to ATOS COM module. ATOS COM module would know where that signal would have to be packed into, because it cannot just send 1 bit of data. So we packed that into a 8-byte, which is the standard PDU, and that 8-byte data is given to the PDUR. And the PDUR will give the data. If it is a segmented PDU, it gives through CAN-TP. If it is not, it directly gives to CAN-IF. And CAN-IF checks the CAN ID, the hardware object, and other settings that are very specific to CAN. And then it gives the message to the CAN driver, and the CAN driver puts it onto the CAN network. If this was the FlexRay message, then the PDUR router, instead of giving to CAN interface, it gives it to FlexRay interface. FlexRay interface puts the data together. So it checks to which time slot the data is going, and then it gives it to the FlexRay driver, and the FlexRay driver puts the message onto the CAN to the FlexRay network. And the same thing goes back the other way around. Whenever the reception happens, the PDU comes to CAN-IF, CAN-IF gives it to PDUR, PDUR then checks whether it has to be given to COM or whether it has to be given to someone else, whether it has to be routed. So it gives the PDU the 8 bytes packet to COM. COM will then know how to unpack how many signals are there, which bit position has what signal, what is the length of the signal. It unpacks, gives the signal to RTE, and anybody on the application side who wants to read that signal, they can read that signal. So this is how the communication part happens inside the ECU, right? I'll skip this. It is again for a gateway ECU, how it works. Then you have operating system. Operating system, again, very important to schedule the tasks, provide memory protection, timing protection. In ATOS, you have multiple scalability classes through which you achieve the safety levels as well. Scalability class 1 provides just a scheduling, whereas scalability class 2 provides you timing protection. Scalability class 3 provides scheduling and memory protection, and scalability class 4 provides everything. So memory protection is nothing but if you want a piece of a specific sensor data not to be accessible to anybody, you can put that in a specific memory area and protect it using memory protection feature in ATOS, such that the rest of the software within the ECU itself will not be able to access it, and they will be able to access it only if a specific permission is handled, right? So that is how the operating system works. To achieve all of these things, there are a lot of layers, right? So to achieve all of these things, you really need a way of configuration and way of execution. That is where the AutoSAR methodology comes into picture. You use something called AutoSAR XML, which is called ARXML, through which you define your communication matrix. In the ECU specification, you define how many signals are there, which signal goes into what PDU, what is the bit position, what is the byte position, whether it's an incoming message or an outgoing message, right? So this is all configured. Using that, you configure your ECU, you generate your executable, and put the executable in the car, in the ECU, right? So when you need to make configurational changes, you go back here, you change it here in the ARXML files, you reconfigure the ECU, and then you regenerate a new bit. That is how the methodology works. And it uses XML as the backbone, but very specifically for AutoSAR, AR XML structure is defined, which has its own tree structures. Going into adaptive AutoSAR, this is how the ECUs have been traditionally, but from there we are going into these ECUs becoming, high performance compute. The body controller, the gateway are becoming one ECU. Instrument cluster, IVI are becoming one ECU. The whole thing becomes high performance compute. Then you have car talking outside to other cars, traffic systems. You have communication, right? Then you have automated driving, where you have different sensors coming around to play. And then you bring in another high compute platform, right? So that way, the ECUs, the cars are evolving, as you saw the complex parts in the previous slides. And this is where the adaptive AutoSAR part came into picture. The classic AutoSAR did not work out. I explained this a little bit earlier, so I'm skipping through a little bit here. And yes, this picture we saw, POSIX OS, adaptive AutoSAR, and then you have the services and the applications built on it. And as we discussed, it is a service-oriented protocol, and it is not a signal-oriented protocol. So that means very highly, I already explained this, right? So I have a service, I broadcast it, I publish that service, there is a service registry. Now I want to, as a consumer, I want to use that service to, another ECU is the consumer here, not a person. So I search in the registry, I find that, okay, the vehicle speed service is available. Then I initiate a request to connect to the service provider, and then I start exchanging the data. If I don't want, I will stop that. Right? Like we saw how the classic AutoSAR part was there. This is the structure for adaptive AutoSAR. You have a virtual machine or a container or a hardware, a Linux ECU or hypervisor that comes into picture. You have the operating system running here. On operating system, you have different modules that are coming in to play. ARACOM is similar to AutoSAR COM that abstracts the communication topics. ARA persistency is the one that covers the memory part. ARA execution covers the execution management. Platform health management is another one. Time synchronization is important. Time synchronization is important whenever you have service-based communication, whether the health of the data is good, whether the receiver and the senders are working in the same time, so that the time stamping is read accurate. So there is time stamping module. There is for the security, there is crypto, and then of course you need to know what is happening inside, so you can configure log and trace such that you get statements out on what is happening, and you can understand the behavior of the ECU. So these are very different layers. So the execution manager, as one of the examples that I'm taking, does the lifecycle management and application lifecycle management. It is not a scheduler, but it manages the whole of it as a platform, right? Applications have to report to execution manager when the initialization was completed by switching to running state. So these applications that we are talking about here, they tell the execution manager that I'm now in the running state. They tell the execution manager that now I am terminating the process. So this way, execution manager really knows what applications are running at what point of time on the ECU, right? Little bit detail of how the communication also happens, right? So one application can talk to another application in the service-oriented method. You have something called events, methods, and fields. You have different sorts of events. You have different sorts of methods to which you can subscribe to, and you can get the data. Routing of service requests, regardless of topological deployment, whether it's service, client applications, RTOM takes care of it. And similar to what we saw in classic AutoSAR, you have also the methodology in adaptive AutoSAR. You have system design coming from the OEM, and then you have different services that are defined by the OEM. From there, you create a service interface. And then you have, depending on the machine-related parameters, you create a machine description ARXML, you create a binary, and here you process an application ARXML based on the services to be brought in, and you bring these manifests, these executable library, you create a package, and then you put it onto the target. So here you can create a package to be used for software update. Then you create a package in that format such that the application can be sent out for a over-the-air update of the feature. Or you put it on your test target, all of your adaptive AutoSAR software, your application software. Then okay, these applications are looking to consume X number of services from the platform to be able to read the data. So which services are posted on the ECU, or which services the ECU is looking to subscribe, this information will come in there. And then you can bake in the software into the microprocessor or the SoC and test, right? This one I will skip. We have spoken about the ARXML and the way things work with the ARXML through the machine manifest, through the service interface definition coming from the OEM. Which is then given to the adaptive AutoSAR stack provider. So then the configuration is done and it is utilized in the ECU. So nothing new here. Okay. With that, I will conclude on the classic and adaptive AutoSAR. But the next 3 slides, I think I just have 3 more slides, are very important. It is not the classic AutoSAR, adaptive AutoSAR that is enough to know of what is happening in the industry. We need to learn, of course, classic and adaptive AutoSAR, but we need to teach the students also beyond that, right? So one of the topic that I wanted to bring is how much of the data processing that is happening in the automotive industry. Of course, on the phone industry or other consumer electronics industry, this is quite common. But in automotive industry, these data are very critical, safety relevant, and how important they are, and how the compute systems are coming in, how AI can come into picture. That is what I wanted to bring here. So from the in-vehicle compute, you are processing a lot of data, right? So those data, you have NVIDIA, Qualcomm kind of chips, which are really powerful. So you get a lot of data coming in. You take those data, you ingest the data and store, you organize the data, and then you train the models based on this data. You test and deploy through the cloud, right? And you build statistics on what is happening with the data. You build dashboards and monitoring systems, and then based on what you do here and what you do here, based on the insights that you have gained, you go back and create new type of value to the customer. So this is a whole new game in the automotive industry, which is not there before. So continuously you're monitoring the data, and then you're utilizing based on you're using that data to give value-added services to the customer. One example I will take quickly, the insurance, right? So for insurance, you need really driver behavior. You need the way the vehicle is being driven. There is a lot of data that comes out of the car that can tell you whether the driver has a tendency to drive rash, whether he's a smooth driver, etc. Right? So that how does the traditional industry of the insurance work, right? So you based on the age of the car, kilometers driven, so you pay a premium and then you are good. Now, I am a very bad driver and you are a very good driver. You take care of your car very well. And I'm not a person who is taking care of my car very well, and I'm very bad in my driving. I do a little bit of rash driving. Then do I and you have to really pay the same premium for the insurance? No, right? So you for being a really good driver who understands your car, you take care of your car, you should not be paying the same hefty premium that I would have to pay. You should get such value-added service, right? And that is one example. So a lot of vehicle data comes in. It is trained and it is assessed in the clouds. Then based on the driver behavior and the vehicle conditions, past year accident data, you can connect this to the RTO systems to get road transport data and everything, right? How many challans have come for this driver and stuff. Then when you buy the insurance, oh, this person is really good, not broken much of traffic rules, takes care of the vehicle, doesn't burn the vehicle out in the driving. So based on his profile, I'm giving a better and cheaper premium because the chances of the insurance company paying after an accident or something is very less for this driver compared to the other person. So that is a value added service, and that kind of things are coming with the data flow like this. And there are many such examples. So automotive is not just about the in-vehicle related parts, right? So you have, these are all the in-vehicle related part. You also have the cloud part. You also have the AI training. You also have visualizations that are needed. But for all of that, of course, the in-vehicle compute platform should be very strong. And that is where our conversation is coming from, that area. But I just wanted to make sure that, we also have a view beyond inside the vehicle alone, right? Software-defined vehicle related challenges. Again, the industry is moving very fast. The government has to catch up. The infrastructures have to come up, right? And then the whole life cycle management of the car is changing. So I'm releasing the software I'm creating a software. I'm releasing a vehicle here, but then I can do a 1.0.1, 1.2.0, another SOP. Consistent, continuous updates are happening. Then I can launch a premium car. So the whole life cycle of the car is completely different from before. Earlier, I decide today that 2 years later, I am releasing this vehicle, and then the work of the project goes in that direction. But now here there is consistent improvement that is happening. The data development is completely changing. The organization way of working is completely changing. There is a lot of Silicon Valley way of working that is impacting. There is a lot of the fastest chip to cloud. The fastest, what is that? It's not chip to cloud. The fastest code to car, right? So I am typing a piece of code today as a developer. How quickly can I bring that piece of software onto my end user? Chinese cars have been very fast in doing that right now. So so that is another important thing. So that gives a whole life cycle change in the way the software development itself happens, right? And to do that, there are certain core technological areas which are very relevant, also for the students, also for people who are looking at automotive industry or looking at building careers in the automotive industry, right? So because of these changes, the architecture of the car changes, right? So you have really strong high performance compute. So after the architecture changes, then you have over-the-air updates through which you can keep updating the softwares of the car. You have smart data. So that means through this, you are also collecting a lot of data of the vehicles. And then you have the cloud infrastructure that is needed. You have location-based services, maps, routing. Robotaxi comes in. So robotaxi needs to navigate through. So you need proper routing for those robotaxis. So the location-based services become very important. Smart sensors are needed. The sensors that just don't pump out the data. Like there are now camera sensors which are not just giving camera feed. It pre-processes the data. It tells me what exactly it is seeing. So smart sensors are important. Artificial intelligence is now coming inside the vehicle and outside the vehicle, of course. And of course, the cloud area, the connectivity, computing backend services that are relevant. So it's a whole new ecosystem of technologies. So I would highly recommend that, look at these areas of where we can, bring the know-how to the students, and help them in building their know-how, and then of course careers in these directions. Yes. With that, I am concluding my part. Apologies, I ate up a little bit more time than what I had planned. I planned to finish off at 7:15, but it's 7:25 now. I'll stop sharing my screen. Please let me know if any questions are there. I would be happy to take for the next minutes. Yeah.
Any questions? Any questions from the participants? You can unmute your mic and you can turn on the video and you can ask the questions to Brahma Chaitanya sir. Any questions?
No questions, madam.
Okay, it's a really wonderful session and amazing topic which has been delivered by Brahma Chaitanya sir. So hope every participant has understood the concept of the today's topic. Any doubts? Any doubts? Okay, hope there is no doubt,
Okay.
sir. Okay, anyhow,
No problem. If there are any questions, if you want to reach out to me, madam has my contact details. I would be happy to connect and help.
Okay. Okay. Thank you, sir. Thank you so much. Behalf of
Thank you,
Sahe
madam.
family, I thank my heartfelt thanks to Brahma Chaitanya Chinnavar, sir, who has delivered the talk on ATOS and network design. Thank you so much, sir, for accepting our invitation and delivering this wonderful session. Thank you so much, sir. Thanks a lot.
Thank you. Thank you, madam. Thank you for the opportunity to be able to talk
Pleasure
with all
to
of
have
you.
you, sir.
Thank
It's
you.
really a pleasure for us to have you, sir. Thank you. Thank you so much.
Thank you.
Thank you, sir. Dear participants, now we have one more eminent person, okay, after session 8, who is Syed Munib-ur-Rahman, sir, who is going to deliver a talk on memory management and queues. To give an introduction of Syed Munib-ur-Rahman, sir, I request Dr. Keshav Murthy, sir, Associate Professor, Department of Electronics and Communication, to give the introduction about the session 8 resource person. Over to you, Keshav Murthy, sir.
Okay. Praveedam sir, am I audible? Sir, Praveedam sir, am I audible?
Hello, Keshav Murthy, sir.
Hello.
Keshav, sir.
Am I audible, Praveedam sir? Komla madam, am I audible?
Yes, sir, you are audible.
Okay. Good evening to everyone present here. It's my privilege to introduce our distinguished resource person for this session, Mr. Syed Munib-ur-Rahman. We are truly fortunate to have him with us today to share his knowledge and expertise on the topic memory management and queues. Mr. Munib sir holds a master degree in VLSI system design from MS Ramaya School of Advanced Studies and a bachelor degree in electrical and electronics from BMS College of Engineering. With over 12 years of professional experience, he has contributed extensively to model-based development, digital signal processing, wireless communication, and FPGA design. He has worked with reputed organizations such as Wipro, Harrisent, as well as Crane Software. Currently, Mr. Munib sir serving as a technical lead at Pi Square Technologies, Bangalore. His expertise covers MATLAB, HDL coding, FPGA implementation, as well as advanced fields like image processing, automotive embedded system, and ADAS technologies. He has played a key role in projects involving electric power steering systems, model verification tool development, and IP core design for high performance DSP and communication systems. In addition to his technical achievements, Mr. Munib has guided and mentored young engineers, developed automation tools to improve workflows, and he has been instrumental in connecting academic research with industry practices. On behalf of the organizers and all the participants, I extend a very warm welcome to you, sir. We are eager to benefit from your vast experience and insights. Dear participants and Praveen sir, please join me in welcoming Mr. Syed Munibur Rahman. Munib sir, now you can take over the session. Over to you, sir.
Thank you. Thanks for that wonderful introduction, sir. It's my pleasure, actually, for the opportunity given to me. Okay. Okay. So let me just start this session with what was actually done in the previous session, actually. So previous session, I believe, was on AutoSAR. Am I right? AutoSAR, adaptive AutoSAR, and a lot of overcloud I think a lot of things were discussed. So this session actually is on memory management and queues. If you look at memory management, right? So let me just start sharing my screen. I hope. So let me know once my screen is, you can see my screen.
Yes, sir. It is visible, sir.
Okay.
Visible, sir.
Okay, fine. Okay, now basically, when you say about memory management and queues, you might have already studied a lot about memories. What is a memory? What is a queue? What is RTOS? Everything. So if you look into memory, I'll not go into too much of basics because you might have already know, most of you. Memory is basically a simple device which can store data. That's what a memory is. It can you can store data, you can retrieve data in that. But if you take a processor requires a memory to handle its operations tasks. So when you write a C code, basically what happens, the code gets broken down into multiple levels. You have stack, you have heap, a lot of things which come into picture. So basically, as you go along, so memory management becomes very critical, especially now we are dealing with automotive, am I right? Automotive systems, RTOS. So why it is critical? So I just have this for breakpoints in relevance to whatever our FDP is on. So memory management actually is an absolute critical in safety critical systems, because improper handling of memory, what happens is, can lead to unpredictable behavior. The system can crash. So whenever you talk about an application, see, there are two types of applications. One application which is safety critical. One application which might not be safety critical. A simple example is, imagine you're watching a TV and there's a controller inside that also. Am I right? If something goes wrong and something system crashes, so your TV will be turned off. So it's not a big deal. So nothing, it's not affecting anyone's life or whatever. Am I right? But imagine if you are driving a car. At that point in time, if there's a failure, so it can be catastrophic. Am I right? It can lead to loss of life, a lot of things. So basically, there are a lot of things in it. Memory management is critical. For another reason, there are two types of behavior. One is called predictability, and the other thing is called deterministic.
Munib sir,
Yeah.
a little bit louder, sir.
Okay,
because-
sorry. I'm really sorry.
Yes, sir. Now it's perfectly okay.
Perfect. Okay, fine. Sorry, I'm sorry. I think.
Okay, sir.
Okay.
Okay, no problem.
So basically, memory management, right? Memory management is critical. The reason being, responsiveness is what is important. See, for example, if there's a crash and if the airbag is slow to open, what might happen? It's of no use. Am I right? So it matters because you need your response of your controller to be faster in terms of nanoseconds. Am I right? And also there is something called memory leakage. All those things needs to be taken care. So without this static memory allocation, dynamic memory allocation, a lot of things. So we'll just go through that one by one. I've just prepared a PPT, and most of it I would be explaining it. So most of the things which you might not find on PPT, I'll try and explain it to you. Okay. Now if you see this, for example, now you have this OS. So everyone knows what's an OS. Am I right? What's an OS? Operating system. Am I right? So what does an operating system do? I hope, I think the screen is visible, right? So there's no issue with it.
Yes, sir, it is
Okay,
visible.
okay.
A good one.
Yeah. So you have a general purpose OS. What it does, there are tasks. An operating system basically is a piece of software that runs on the computer or a controller. And there are a lot of tasks which are running in the background. And basically, it is user driven. Am I right? You'll have several applications. You'll have several applications which are running in. So you can consider when you're opening your OS, you open Windows, you open Word, you open presentation, you're trying to open some other player, all those things. So these are called tasks. Okay. So all the tasks, there is scheduling happening. So how the scheduling happens? So that's what is the task of a scheduler. Am I right? So basically, how does it executes? How things gets executed in your system. That's what these tasks are. So if you go to the next slide, basically you have this resource management. So when to write, when to read. So, okay, I'll just put, now you have, if you see this OS is parallelly interacting with all the things at a time. So you might click a mouse, it has to perform the action of left click or right click. Am I right? And at the background, you have tried to open a file. So basically the tasks run in a manner, one by one. So polling method or whatever you can call it. So this is how a general OS works, right? Now, these are just the key points. Now, the general OS is human interaction based as the most prominent feature, so that the scheduler is designed to prioritize each task. Timing deadline can be missed or pushed back. So this is what is an important point. So what's the timing deadline? Timing deadline is, for example, if you open a file and if it gets a bit delayed, or it might take a time to open. Why? Because there is some other task which is assigned. So if all the tasks are in a pool, and that's the reason we call it as non-deterministic. So can anyone say what is deterministic and non-deterministic? Any idea? Anyone? So actually deterministic, right? Refers to memory management where the timing and behavior of allocation and deallocation are fully predictable. In simple terms, it means that you can guarantee how long it takes to allocate or free memory, and you know exactly what happens. Am I right? So in real-time scenarios or safety critical systems, you need to meet strict timing deadlines. Unpredictable memory, like dynamic memory allocation, like you have calloc, malloc, can cause delays. Am I right? So in your OS, whatever you see, you have non-deterministic scheduling which takes place. Now let's talk about RTOS. So what's RTOS doing? What is RTOS doing here? RTOS is nothing but you have a deterministic timing behavior. What is the primary goal of RTOS? You need to understand it. What is the primary goal of RTOS? Because without the primary goal, if you don't understand the primary goal, you might end up not understanding the concepts around RTOS. Am I right? So all these sessions, whatever you're going, is all about the RTOS, right? So everything is tied to if your automotive systems, everything. There's an RTOS running on it. Am I right? So The primary goal here is RTOS ensures that the task meet all the strict timing deadlines, whereas your general OS will maximize system throughput and user convenience. It doesn't bother much about the tasks. And timing is not critical in your OS, but it is critical in your RTOS. So that's the reason you call it as deterministic and non-deterministic. So RTOS has a deterministic behavior allocation response time, and the latency is low. What do you mean by latency? Latency you can count in terms of clock cycles am I right? So your auto system scheduling, you are scheduling, task handling, interrupt handling, lot of things, am I right? Happens on the deterministic behavior. So examples of your general OS is your Windows, Linux, Mac is your general OS. When you talk about RTOS, you have free RTOS, you have VxWorks, you have QNX. Am I right? So what are the use cases of OS? The use cases of OS are desktops, servers, phones. The use cases of RTOS are drones, your medical devices, your ECUs. Am I right? So with that thing in mind, we'll just move ahead. So as you can see here, when you have a specific task to be done in a specific time, you need an RTOS and you need a proper memory management to it. Am I right? So I just have one simple example. Whatever you see here in this loop is a generic behavior, generic OS behavior. You have task 1, task 2, task 3, or these tasks are running in a loop. So it's called a super loop. Task 1 is done, then task 2 is taken up. After task 2 is done, task 3 is taken up. And if you want to perform some priority-based task, you want to perform a priority-based task, at that time, you have the option of ISRs, routines. So what is an ISR? You all know it's an interrupt. If there is an important event which comes up, so your tasks has to pause and can go attend that ISR and come back. Am I right? So if you need to meet a timing deadline of less than 1 millisecond, interrupt is the best way to implement. But if that interval becomes less than few nanoseconds, you either need an incredibly fast processor or you have to look into some other hardwares like an FPGA. Okay. Now let's talk about RTOS. So in RTOS, if you can see, the tasks are parallelly executing. So you need to understand just these terminologies you might come across. So what is a task? Task is a set of program instructions which are loaded in memory. Thread is a concept of CPU where a unit of CPU utilizes its own program for that. Process is an instance of computer program. Anyways, so I'll just now because see there's a difference. Always there is a confusion like a CPU with multi-threading. Is it same as an RTOS? Basically, CPU with multi-threading allows multiple threads to share the same physical core. So the hardware is rapidly switching between two threads, making an illusion that it is running in parallel, which is actually not. So in RTOS, the tasks are like threads. So the RTOS scheduler decides which tasks run at a given time, often using priorities. Okay. Now, if you take this thread in CPU and task in RTOS, there is a similarity to it. So both are lightweight execution units, both have their own stack, both need scheduling to share resource. Okay. Now, when you come to the differences, you have CPU, which CPU hardware utilizing multi-threading. What is multi-threading? Again, it's an OS concept at the hardware core level. RTOS task scheduling is at the OS software level. Okay. Again, we'll take up an example. We'll start off with an example. Now, I have a modern day car. So do you know how many ECUs are there in a modern day car? If you take a modern day car, so there are a lot of ECUs in it. So can just someone say a number? Okay, how many ECUs are there in a modern day car? Just a number. So what's in ECU basically? EC is your electronic control unit. So what's an electronic control unit? Anyone can either. I just wanted to be a bit of interactive session so that, or if you can just type in, if you want to answer, you can just type in and send via chat also is fine. So ECU basically is a controller. Okay, now you have a modern day car. So in the modern day car, you have multiple ECUs. So what are these multiple ECUs? You have ECU for critical control ignitions, fuel injections, and you have very high priority ECUs for ABS. ABS is your automatic braking system, brake sensors, and there are some low priority things like your infotainment. Medium priority is your climate control. Now, out of all this, which is given more priority depends on the criticality of it. Okay. Now just have a look at this. Take your time and just have a look at this. Now, if you see this table, right? ECU, the task description and the priority. Now, brake sensor. What is the description? Your pole brake pedal, wheel speed sensor. What is the wheel speed sensor? It's the speed of a vehicle. So basically that ECU will have the highest priority. Whenever any communication happens from that ECU, it's given the highest priority. So next you have the ABS control, then you have other engine sensors data, all those things. So these are all RTOS defined tasks and priorities. Now, let's take a scenario. Critical task preemption. Now, for example, normal driving, engine ECU task running, climate control infotainment is updating. Second, sudden brake pressed. When you press a sudden brake, the ECU gets the highest priority, which triggers your ABS control, RTOS, preemptive engine, AC and info. Preemptive engine, AC and infotainment task means the other tasks are pushed back, and this task is taken to the top priority. Okay. Now what are these key concepts in this scenario? So basically, what I'm trying to, okay, maybe this diagram might be better. So what I'm trying to tell is all these ECUs are communicating via a CAN bus. All these ECUs are communicating via a CAN bus, and there's a scheduler. So which, if you, I think the CAN session will be covered probably in coming sessions. So maybe I'll just give a brief of it. Not so basically every CAN message has a priority. Which message or which task gets the priority depends on the CAN frame. Now, based on the priority, the tasks are scheduled. So I'm just trying to give a brief background about what is RTOS, what is OS, what is safety critical applications, which gives what is priority, all those things. Now let's jump into memory management. Okay, now this is what is our topic. We are coming to our topic now. So what is this memory management in operating system? So I'll just try to go to this diagram. I don't know how many of you remember this diagram. So what is this diagram? What do you understand from this diagram? Any? So this diagram basically is an allocation of a program. Whenever you write a code in your C code, you have various parameters, right? So can someone tell me what comes in stack? What comes in stack? So whatever diagram you see, probably if someone can just I think, okay, sorry, I think the diagram has not come. Okay, yeah, this diagram. If you see this, right, every memory has an address, say 00000 to FFFF. It depends on the size of memory. So you have stack, heap, you have data segment, you have code segment, you have BSS. Am I right? So what is stack? Basically, stack is something which stores your local variables, your function parameters, your return addresses in a code. I have an example moving forward. I'll show you the example. So what's a stack? Stack is something like storage of your cross compare. Whenever you write a C code, the code gets converted to your machine language. All that is stored in either stack or heap or data or text. Am I right? What's in heap? Heap is something like when you allocate memory, there's something called as scalloc and malloc. When you allocate memory, the heap, that part of it gets stored in heap. Am I right? So it grows upward, as you see the diagram, no? It grows upward, and memory leak risk is there if it is not freed. What I mean to say is, whenever you write a code, for example, you write a code and you write, you initialize a variable. For example, okay, let's talk about it. Example, if I take int x is equal to 5, where does that get stored? It gets stored in your data. If I take a variable int x5 float. Now what is BSS segment? What is BSS segment? BS segment is a portion of your program memory where uninitialized global and static variables are stored. Uninitialized? Okay. So that's your BSS. Am I right? So basically, whatever you see here, I'll take a simple example. I'll just take an example of, let me take an example and show it to you. Okay, I hope you can see this. So for example, if I type a code, I'll just show you. Include okay. Now this part, now you have your static int, static variable. Now this comes under your data segment. This comes under your BSS segment. Now if you come to your program, int main, you have this int local variable is equal to 5. This goes in your stack. Am I right? Now what you do is you try to define int star dynamic variable where you allocate this memory malloc size of int. That's the syntax to do it. Am I right? So this comes under heap. So what is the difference between this and this? This is fixed. Int, you're assigning certain section of memory, but once you do this dynamic memory allocation, it allocates it at the runtime. So whenever you are allocating a dynamic allocation after that integer is used, that needs to be freed. So what do you mean by it? Does anyone know, example, what is calloc and malloc?
Dynamic memory allocation techniques, sir.
Yes. So you have calloc versus malloc. So you need to understand what is calloc versus malloc. Is dynamic memory allocation allowed on a controller? Yes or no? First, let's try to understand what is meant by allocating memory. So okay, whenever if you take a simple in your computer, you're running VB, and you are writing a code and you are compiling it. So you can just test it out. You can try to allocate a memory and try to allocate size of int. You can just check it out. Your resource memory allocations. How much it gets assigned in your memory. If it is not freed after you have run, your system also might crash. So basically, what I'm trying to say is allocation of heap is malloc is one form of memory allocation which needs to be dealt with proper care. Am I right? So you can even check it. For example, I'm just taking, I'll take an array, for example, int array. I'm just taking this. For example, I can check this. If array is equal to null, if it is null, it means that allocation has failed. It didn't get allocated. Okay. So you can have a check of allocation. Basically, why are you allocating? Why are you allocating this? Why? Because I might be using this variable ARR here, for example, for int. I'm just taking a simple example. Pardon because I'm not running the code, so don't ignore the typos. Now, if I see this of I, I'm trying to array of I. I'm trying to read some data here. So this n, no, it's getting built up. So this segment of code goes in your heap. This segment of goes in your heap. And whatever allocations you have done here, that goes in stack. And whenever the program is compiling, right? So what happens is your stack and heap keeps on growing. Your stack and heap, maybe I want to show it in a better way. So what happens is the heap can keep on growing and the stack can also keep growing. So do you see this arrow? You see the arrow at stack coming down and heap going up. So what does it indicate? Any idea? Because it's a very primary thing. Whenever you write a C code, right? We just write a C code without taking care of this point. We don't consider this much. Anyways, so basically memory allocation happens based on the code what you write. And whenever you're writing the code, you should be very clear that how much heap or how much stack is allocated at the runtime, and how many variables are fixed at the start, and how many variables can grow. So what are the dynamic memory allocations or dynamic variable allocations will all come in heap. All your local variables will come in stack. Am I right? So stack frames actually are pushed onto the stack during function calls. So each new frame, local variable or return address, is placed at a lower memory address than the previous one. That's what this concept is. So you got the point, right? So every new variable, this is your high address, and it keeps on going below. So whenever, for example, if you take int x, this gets stored here. And when you call a function, this gets pushed and it keeps on going down. So that's how the stack happens. So whenever you decide how much memory is needed, so I just have one example. I just want to show it to you. Maybe anyways, until it opens, let us run this. Now, this allocation of memory is prime importance to the controller, because what happens is your controller, right? You have your microcontroller. Sorry. You have your microcontroller. Or processor, what do you think? Okay. So this is basically tied to your memory. Am I right? So whenever you write a C code, this gets sit here, and the memory, the controller is accessing this memory, fetching the codes and running it. So you need to understand how this allocation works. I have an example later on. I'll just show it to you. Let's move ahead. Okay. So again, so what is memory management? It's again memory management with respect to OS. Okay. Now already we had seen this. So memory management is a crucial aspect of your OS, which ensures that your computer resources are used, allocated and deallocated in a proper time. Okay. Now you have, I'll come back to this slide later on. I just want to go for this example. Can you see this now? Now, if you see this diagram, this is, I've simplified it. I've simplified it for you. Yeah. So if you see this code, right, whatever which is declared above the function, your int global variable, static int local, everything goes in static part of the RAM. So that's your static allocation. This part is clear, right? Okay. Now you have automatic allocation. Now, what is automatic allocation? All your function arguments, your integers which are defined inside a function, that goes there, and your heap is where your malloc happens. So this is one of the most crucial part of your aspect of your memory management. Whenever you are writing a code, right, where and how much memory is needed for this particular application to run. Why I'm telling you this? Because in safety critical applications, it may so happen that your stack or heap might start to leak, or it might start to overrun the memory. In the sense, you have defined 16K of memory, it might take more than that. At that time, the system will crash. So these memory aspects of it should be defined. So that is the reason there is something called as memory management. I'm sorry, I think I'll sorry, 1 minute. 1 minute. This. Am I audible? So, I'm sorry. I think there is. I'm
Audible, sir. You are audible.
sorry. I'm sorry. Okay, fine.
Audible, sir.
Yeah.
Audible, sir.
Okay, sorry. I think there was some issue with my headphone. Fine, no
Little bit louder, sir.
yeah,
Because,
fine. No
yeah.
problem. So basically, this what? So you have static and dynamic allocation. This choice between static or dynamic is based on your computer program being developed. If you have to load your program statically, then at the time of compilation. What is compilation? When you write a code, the compiler converts your code. So the compiler program will be compiled and linked without leaving any external program or module dependency. So basically, your code should be written in such a way that your memory allocation is done parallel. No, this is with respect to a regular system. Now let's come to your OS memory allocation. Now, what happens in OS RTOS memory allocation? How different is RTOS memory allocation than the regular memory allocation? Now you need to understand this. Key. What is memory allocation? You understood so far. Memory allocation is nothing but your code gets compiled in segments. Okay. Now, what is your memory allocation with respect to RTOS? Basically, what happens is in your RTOS, there are subtasks created. So TCP is your task controller block. So in this heap, you have individual tasks created which cater to a specific application. Am I right? So what is this TCB? So you have task 1. Then you have tasks 2. So these tasks are allocated inside your heap. Am I right? So, and this are managed by your threading. That's how it is. Okay. Now, let's talk about memory challenges. So what are what are challenges which typically are faced when allocating a memory? So when you have limited memory resource, what do you do when you have limited memory resource? So what do you mean by limited memory resource? Is you have just 16K of RAM, and when you try to overuse it, so you should be effectively using it so that your code will not overrun the memory. That's what it is. Okay, just a minute. So okay, so you have fragmentation. So what is fragmentation? Fragmentation, defragmentation. Fragmentation is whenever you're using a lock, that part of memory gets allocated to it. So if the memory is not available at that point of time, so there might be an issue. So what is unpredictable allocation time? So whenever you're trying to allocate a memory, and if there is some other application which is trying to use that memory, that's what it is. Now, when you come to the safety standards, now that's what is important. When you come to safety standards, you have MISRA, AUTOSAR. So what is MISRA? Can someone tell me what is MISRA guidelines in C code? Has anyone used? Has anyone whoever does the C code, do you follow the MISRA guidelines? So what is the full form of MISRA? Can someone tell me? Anyone? Just I think even the full form of it is fine. Full form of MISRA. MISRA basically stands for Motor Industry Software Reliability Association. Basically, it's a coding standard. It's a coding standard which is being introduced, which follows guidelines. Whenever you develop a code, whenever you develop a C code, how much of the code, how many functions should be present, what to use, what not to use. Can we use dynamic memory allocations? Can we use pointers? So can we use what do you say? What is the complexity of the code? What is the language scope of the code? So whenever you write a C code, there are various parameters to it. So some of the parameters are, if you see, there's something called as number of paths in a code. So what is number of paths? If your code is too complex, it might consume a bit more memory than the regular thing. If it all depends on instructions. Whenever you write a piece of code, it all comes down to your instructions usage, how your instructions are mapped to the memory. Okay, so now okay, 1 minute. I just have another presentation. I'm just trying to open. Just give me 1 minute. Okay, I'll come back to this bit of memory management. Now let's start looking at what is a queue. So what is a queue and how a queue works? So to understand a queue, let's try and understand a memory. So for example, I have a memory and I have a queue. So what is the difference between a memory and a queue, and how are these similar or are these different? So how does a queue differ from a memory? Because basically queue is nothing but a memory, but how the interaction happens. So basically you must have heard something called FIFO. You have FIFO, you have LIFO, am I right? So can someone tell me difference between a RAM versus queue? I would like an answer before I proceed. Anyone can tell me. Whatever I have put in, does it make sense? What is a queue and what's a RAM? Because you for understanding the concept of queue, you need to know what's a queue and how different is it from a RAM, or is it same as RAM? I don't want to. Okay, sorry. I think I've just. I don't want to use the PPT. I just want it to be. I'll explain it directly on the board. So, can someone tell me what is a RAM and what is a queue?
Sir, in queue, data is stored in a specific order.
Yes.
Whereas in RAM, in my perspective, it is like randomly whenever the temporary variables are they have been replaced. So in that place, data is going to be stored.
Exactly. Yeah, you're right in a way. You're right. You're right, ma'am. So
Yes, sir.
just to make it a more simple understanding, I just tell RAM has input address. RAM has input address. Am I right? Whereas queue or a FIFO, does it have an input address? Yes or no? It has input address and it has input data. It has data, it has address. What does a FIFO has? FIFO or LIFO, what can you call it? What does it have? Just the signals. As ma'am told, like in memory RAM, you can store data at random locations. Am I right? Can we do that in FIFO? So you need to understand that. I just want this. I just want to know if what is the input to it. Now I'm telling you have data, you have address, maybe you have an enable. So what are the inputs to a queue? What are the inputs to a queue? So queue has just the data, am I right? It doesn't basically necessarily have the address. What do you mean by it? In RAM, I want to write in location 36. I can write the data here. I want to write in location 5. I can write it here. I want to write in location last. I can write it here. But FIFO doesn't or LIFO doesn't work that way. Whenever the data is pushed, it comes and sits here. When the new data enters, this is moved down. Imagine I wrote 1. The 1 has come here. I've written 5. The 5 comes here. So when I write a new data, so it keeps on pushing down. When I read data out, when I read the queue, what was entered first will go out first. That's why it's called a FIFO, first in, first out. So what is LIFO? So if I've stored in a FIFO, if I've stored, say example, 1, 4, 6, 10, 22, 56, 18, example I'm giving you. So whenever you read it, the order is the same. Whichever came first goes out first. In LIFO, if I've written 1, 4, 6, 8, 18, 89, whenever I read, the last part is used. So this is the difference between a queue and a RAM. So if you want to just note down the differences, if I want to just finalize the differences. So basically, it's an hardware memory in your embedded systems. It stores your data instructions temporarily while the CPU is running. Am I right? So it's fast and it's volatile. So RAM allows random access basically. So what happens with queue? It's a data structure. If you talk about, if you come to low level, whenever if you're writing in C or if you're writing in Verilog, it's a low level. It's a data structure which is used in software. It is used to manage tasks, messages, data buffers in software systems. It's implemented using arrays and linked list. There are buffers, circular RAMs, a lot of things. Am I right? So if you want to understand a simple example of a queue, has anyone written, does anyone know what's a linked list? Just the definition. Linked list. What is a linked list?
Unlike stacks and queues, data can be accessed anywhere in between also.
Okay. Okay. So linked list is something like you have a code and the last part of the code will link it to the new segment. Okay. So anyways, no, is the difference clear between a queue and a RAM? So if you have to write a C code structure for a queue, very simple example for a queue, how do you write it? Because it's because see here we are talking about primarily a C code. You have difference in C++, you have difference in your what do you say, in your Python or whatever. Now, if you want to just write a simple code, I'll just trying to help you out with a simple structure queue. Now you have, what is the items? You can define the size of it. Rear or back. Okay. So this is the structure of a queue, how it is. Now you can define a function int queue where you can define a pointer to it. So basically, you can write a C code, you can write a structure, you can define this size, and you can write the code for it, and you can try to push data to it. You can store data and you can retrieve data. So a lot of things can be done. Now, coming to queues, how queues and memory allocation. So what is the relationship between queues and memory allocations? Because our topic is memory management and queues. So how are both related, or are both separate, or how does the relationship works between a memory management and queues? How it is basically. So what is queue? Someone asks you, what is a queue? At a very high level, queue is nothing but a FIFO. Good answer. Yeah. First in, first out, or last in, first out. That's how it is. But if you want to define it at a very low level, in terms of code. So queues are nothing but as, if you talk about C language, what is a queue? Queue is nothing but, what can you say? If you want to, just now I told you the example. I just did a code now. Queues are data structures that requires memory to store elements. Am I right? Queues are data structures that require memory to store elements. The memory is managed after once it gets stored. That's when the memory is managed. So basically, queues depend directly on memory management to work efficiently. That's what it is. So try and understand this. Your queues are data structures that require memory to store elements. Am I right? So that memory is again managed later on. So queues are stored in RAM and memory. So basically, and memory for them can be the static, dynamic, or stack based. That's what it is. Okay. So one moment, I just have one example. I'm just trying to open. Can you see the SDK screen? Can you? Okay. Can you see this code? Yeah. Can you see this code? Hello? Hello? Okay. I think my voice. Basically, I'm just trying to show you the memory allocation, how it happens, and what are the things which are allocated. Okay. So can you see this? So it's basically a memory map for a cortex, ARM cortex, and you get the base memory, and you get the 1 minute. These are all the various peripherals. You have QSPI, you have USB. This is basically memory map for your Cortex CPU. Okay. Now, Application project. Okay. Okay, see here, I'm just showing you an example of SDK what I presently have. There's something called as bare metal versus non-bare metal programming. So whenever you have a controller, you can write a C code and that C code runs on the controller and you get the required output. So it's purely a C code. The OS platform is standalone. There's nothing on it. So if you try to select free RTOS, so do you know what's a free RTOS? It's one form of the RTOS. Am I right? So basically you can define your application, test application. Next. So you have this free RTOS Hello World application. Click on this, finish. But it's taking a bit of time to open. I thought I'll show you an application actually. Okay, now can you see the free RTOS code, Hello World C code? Is it visible on your screens? Or okay. Now, if you can see this is a very simple code which works on your free RTOS. So if you see here in this, there are lots of tasks. And here, this part I wanted to show you the memory allocation here. You have text, you have data, you have BSS, you have all this here. Am I right? So this test app.elf, this is the memory allocation for this. This can be changed or configured. It depends on, now right now I've taken default. Now if you come here, these are your free RTOS includes. So free RTOS, if you know, I don't know if anyone has used free RTOS. So it's open core, you can use it. So basically in that, you can create various tasks. The queue used by TX and RTOS are described at the top of this file. Am I right? Now these are your task handlers, timers, and how you can determine the task creation, the task execution, the task queue, the timers, the interrupts, all those things. Now, if you want to go have a look at it, what this task create does. You can just right click 1 minute. Open declaration. If you can see this. So allocation. So what is the allocation? So if it's a dynamic allocation, how you can allocate it, what you can name it. So all the things can be mentioned here. Okay. So basically, I know this code might look a bit complicated for you to start off with. Okay. I don't want you to go into details of this code. What I'm trying to show you here is the allocation, how it happens, can be defined by the user. Okay. And this is if I've opened this code, the moment I open this create, there's a tasks.c and there's a task.h, which is already there in the include. So if you can open this, this is provided by FreeRTOS kernel. Now here you can see the list of task parameters, task status, priorities, critical, interrupts, all these things, schedulers, so which are already defined in this .h. So whatever is defined in this .h, that can be, we can use this in our program here. Okay. So I would like to show you another example here. I'm just using an Xilinx tool. I'm using a Xilinx tool to help you understand how memory can be defined, allocated. Now I'm just defining a microprocessor is, you can call it as a controller, which you can do it on an FPGA. Okay. Now if I double click on this, so here, so I can define the local memory, all the memories, whatever I want, the mode of communication. So I'll do one thing. I'll just do run block automation. So I'm just trying to build my own controller with specific memory requirements, whatever I need. Now, if you come here, local memory, 128 KB. So it's up to you to define the memory. Now, if I think whatever I'm showing you here, this code, this application, if this application demands that whatever code I have written, maybe an hello world application, whatever you see here, might be a non-RTOS application, might just take 2K of memory. But this application, test.app, might take more memory. So whenever I'm defining this, so I need to define my local memory. Local memory actually will depend on your code, the size of code. The size of code, how much code you write. So basically define. So I can take 32 KB example. Okay. Now you can just leave it as default. I'm just click on OK.
ಗುರುನ ಏನು ಮಾಡಲ್ಲ ಸುಮ್ಮನೆ ಆಗ್ಬಿಡ್ತಾನೆ ಗುರು ಗುರು
ಗುರು ಏನ್ ಮಾಡ್ತಾನೆ?
So, okay, let it open. Until then, I'll just try to explain what is this task create. Okay. So what is this task create here? If you see task create in this. So a task in a FreeRTOS is again lightweight thread. It's an independent unit of execution created and managed by FreeRTOS kernel. Now, if you see this task, there are various things. What are the key concept of this task? It can do multiple tasking. It can do priority-based deterministic scheduling. Each has its own stack size, and each controls which task run next, the scheduler of it. So these are your key concepts. Now, once, for example, this whatever task is created, right? So this task, I can name what task it is, and I can pass various information to it. So I can create one task. Only two tasks are created here. I can create 3, 4, n number of tasks here. Am I right? So once I create the task, every task has certain parameters. So what is this PVR task? What it does? What is the stack size of it? Okay. What is the priority of it? Am I right? So this is your, whatever you see, this is your task function. Okay. This is your task name, which is used for debugging it. So this is your task size. Okay. If you open it, I think you have allocated the task size somewhere at the top. This is your task size. So basically this task parameter is not used, and this is the priority. So this PVR task, this is a function that implements the task. Am I right? This is the function that implements the task. And this is the task name. TX is your task name. Am I right? And this config minimal stack size is usually defined in free RTOS config.h. Okay, it defines the minimum stack required in a simple task. If your task uses more locals or call functions, so your require stack, you need to increase this. Then you have task parameter. This is task parameter null. So means you are not passing anything. Now, this is your priority. This TSK ideal priority means that the task has the same priority as the ideal task. If other tasks have higher priority, this task may not run until they are blocked or they are suspended. Now, this is your task handle. Am I right? Now, for example, if you want to write a task function, this is my PVR task, right? No, you would see that there would be a task function written somewhere. 1 minute. Okay. Now, if you find this, so if you want to just write this task function, I'll just write it here. Void task. Void send data. Okay. So this is the example of a task function. Am I right? So in this way, you can create various tasks, and every task can be handed a priority. Every task can be handed a size allocation, and every task will have an handle to it. So based on the priorities, the task will be scheduled by your scheduler. Am I right? Now imagine there's a scenario. There are two tasks. There's a TX task and there's an RX task. I'm talking about the scheduling now. So you have TX task and you have an RX task. So TX task has ideal priority. RX task has higher priority. So what do you mean by it? So both tasks runs at 100 millisecond. So when to define what? It basically is up to the user to do it. Now here, whatever you see, just an hello world example, what I can do here is I can create my own task, 10 different tasks, assign 10 different priorities, and try to put it on your controller and try to connect sensors to it and try to execute this code and check out if my tasks are running as per the priority given to it. Okay. Again, it's very difficult for you all to maybe understand everything in a very small session. But my idea of telling you is that whenever you write a code, because it all boils down to your code, how you write a code. Is your code a bare metal code or a non-bare metal code? I'm just trying to pause here, stop here, and just try to refresh a bit of your C and embedded OS concepts. Now, whenever you write a C code, suppose for example, I have an ARM Cortex. I write a C code. This C code, I dump it on the Cortex, and there is no OS on it. So this is called as bare metal. What do you mean by bare metal? Bare metal means there is no OS on it. So everything is controlled via the code. Am I right? So now when you talk about non-bare metal, what happens? Can someone tell me what is non-bare metal? What is non-bare metal? Non-bare metal means an OS will be running on this ARM Cortex. So the moment OS is running on this ARM Cortex, and this OS can be either it can be a regular OS or it can be an RTOS. So that's what I was trying to explain here. If I take new application here you can see OS platform, either Linux or standalone or free RTOS. So this is the OS platform. So once you have this OS platform, based on whatever code you write. Now, if I take standalone, for example, and this is the processor. If I take standalone, you have this hello world. Okay, now this whatever you see here. So it's a bare metal code which doesn't have any OS on it. There's no priority scheduling. There's no task. There's no queues. It's just a simple C code which runs on your controller. Am I right? And now if you see this code, FreeRTOS hello world, it is different from what you see. Why? Because this has tasks. This has every task has different handles, and the user can define how many tasks to create, which task to priority, and what each task does. And everything, all this is tied up to the memory, how much you allocate. So in the end, it's up to the user to define the memory allocation, define the code, and manage your code effectively so that your code efficiently runs on your controller for a safety critical application. So here in our example, the safety critical application is your automotive or aerospace, what you are talking about. Okay. Now, if we try to summarize it, what have we been discussing so far? So can someone just tell me what is memory management and how it is related to your RTOS, and what is Q? Q is a subset of it. So basically, if you want to just summarize it, memory management is essential in writing a code which can run at timing guidelines, which cannot be, what do you mean to say? Like deterministic behavior. Okay. So your memory management depends on the task what you're dealing with. Okay. So does anyone have any question? If you can have any questions, probably you can just ask.
Any questions, participants?
Okay, I'll just like to uh, have a small ending to it. So what are the takeaway moments here? So what are the takeaway moments? So you have memory management. What is memory management? We'll just try to understand this in very simple words, just to end the session. We have number point one, memory management. So what is memory management? It's pre-allocated memory pools, which ensures that deterministic and safe memory usage. When to use dynamic? Is dynamic allocation possible in runtime or safety critical applications? Yes or no? Proper stack sizing, the buffer management, and monitoring of the calls or crashes. Second important point is queues and task communications. So what are queues? Queues provide your safe thread FIFO communication between tasks. So you have tasks with high priorities, low priorities, blocking versus non-blocking, priority aware queues, and proper sizing of queues. Am I right? Then all this is basically integrated typical flow of your ATOS arrays based on your CAN protocol. Okay. So please, if you have any questions, you can ask.
Any questions? I think no question. We sincerely thank Mr. Syed Munib sir for his insight session on memory management in RTOS. His clear explanation and practical insight greatly enhanced our understanding of the topic. So thank you very much, sir.
Thank you. If at all anyone has any doubt pertaining to you can reach out. You can reach out to me because strictly speaking, uh, 90 minutes of session trying to cover what to cover, what not to. It's a very small amount of time to talk about it. So I tried my best to give some examples. But again, thank you.
Thank you, sir. Thank you very much, sir. It takes a lot of time to understand more things about this. Thank you very much, sir. Okay. So I ask the participants to switch on the cameras so that we can take the snapshots. Okay. I thank all the participants. Okay. So on the same 6 o'clock, once again we'll join on the session, tomorrow's session. Thank you.